semiconductor. So as soon as these two type of semiconductor, it is the same semiconductor but doped differently. As soon as a p-type and n-type semiconductor is joined, many interesting things actually takes place. They take place, and so so there are many players here. One is the majority carriers on each side. Second is minority carriers, and third is the static charge carriers. So these majority and minority carriers are the mobile charge carriers, and the dopant atoms are the static charge carriers. So they cannot move, and but these mobile charge carriers, the minority and majority charge carriers, can easily move around. And that's what they do when we join a p-type and n-type material. Because of the diffusion, majority carriers go to the other side and recombine. And this leaves a lot of uncompensated dopant atoms, both donor and acceptor, and that makes the depletion region. So these are various type of particle flows here. From p-type, we have hole diffusion and electron drift. This electron drift happens because now in the depletion region, there is an electric field and a contact potential. And similarly, from the N side, we have hole drift and electron diffusion. So the diffusion of majority carriers and drift of minority carriers. That's what happens when we join uh, when we join p-type with n-type, and in equilibrium, which means we have not applied any external voltage. And uh, how do we define equilibrium, by the way? Anybody can comment on this?
So net zero change
when
in
the
concentration of current.
sir
Yes,
when
yeah, somebody else. Yeah,
when the two
yeah,
opposing
please.
processes of diffusion and drift occur at the same rate, or when the drift current and the diffusion current become equal.
Yeah, so broadly it is correct, but generally in thermodynamics or in statistics, equilibrium is defined as the state of system in which every process is balanced by a counter process. So there might be various processes inside the system in equilibrium, but each of those processes is balanced by a counter process. So in this case, every type of flow is balanced by a reverse flow, both for electrons and holes, and that's how we define equilibrium in the case of diode. But more generally, when every process inside a system has a corresponding counter process, reverse process with exactly the same amount, same rate, then that state is known as the equilibrium state. And there is this another concept, the concept of steady state. What is steady state?
No additional increase or decrease in the process.
Yes, exactly. So when, yeah, somebody else was there saying something.
When the rate of any process become constant.
Yes, exactly. Yeah, that's how it is defined. When, as you said, when the flow or the rate of the process in any direction becomes constant, it does not change with time. That is known as the steady state. So the state in which the current is constant in the system is known as the steady state. And transient state is the state when the system variables and processes are dependent on time. So all those kind of things happen in diodes as well, actually. But we are concerned, so at the moment when we join these two type of material, suddenly transient state is there, then very quickly equilibrium is achieved. If we apply external voltage, then we have steady state. Okay, so just keep these things in mind. In our last class, many of you had actually various doubts about where is the charge, how the charge is distributed, how the electric field is distributed, and what is the width of the depletion region, how is it dependent on the doping. So I have put all these things in this slide. So we have this. This is the diode. This is made by joining p and n-type materials. So this concept might be new to you, I guess. This is the band diode. This one. So we cannot go into too much of detail of the band diagram here, but I'll give you an overview so that things are a bit clear. So, so both of these are semiconductors. Both p-type and n-type materials are semiconductor materials. So both of them have valence band and conduction band. So that's what we have plotted here. On the n side, this is the conduction band, bottom of the conduction band, and this is the top of the valence band. On the p side, this is the conduction band minima and the valence band maximum. And this yellow, sorry, this blue, light blue line, dashed line, is the Fermi level of the system. So this, the notion of Fermi level is actually, it comes from statistics. So, so please don't worry if you don't know the origin where this is coming from. But let's, for the moment, let's just assume that there is a Fermi level in the system. And
Sir,
there is,
can
yeah,
you use pointer, sir? We are not able to see where you are pointing.
okay, so yeah, let me, yeah, it should be, is it all right now? Let me use a pen. So this one, these this light blue is the Fermi level. Now is it all right?
Yes, sir.
Yeah. So yeah. Thank you for pointing this out. But so if there is any such concern, please let me know in between. So there is a property of Fermi level that we need to remember, and that property is, and that comes purely from maths. So it's not that it needs to be sort of remembered. When we do maybe in your coming courses, if you, when you do the actual analysis of Fermi level, you will see this. But the difference between the valence band maxima and Fermi level, this difference actually governs the number of holes in the system, which means that if this Fermi level is closer to the valence band minima, there will be more number of holes in the system. Okay, and similarly, the distance between the Fermi level and the conduction band minima, this governs the number of electrons in the system. So the distance between this and this will be the number of electrons. So less is the distance, more is the number of electrons. More is the distance, less is the number of electrons in the system. Okay. So and in equilibrium always, and this is a principle of thermodynamics, the principle of detailed balance, that in equilibrium the Fermi level of the system is constant. So that's why the Fermi level is a single line. In steady state, this Fermi level may not be a single line. On n side, we might have a different Fermi level. On p side, we might have a different Fermi level in steady state or in transient state. But in equilibrium, it must be uniform across the device. Okay, so these are some basic things about the Fermi level and band diagram. Now, this is the equilibrium band diagram of the diode. And as you can see, far away from the depletion, far away from this junction, far away from the depletion region, here, this Fermi level is quite close to the conduction band minima, and number of electrons is huge in n-type material, which is what we expect as well. Similarly, in p-type, p side, far away from the junction, Fermi level is quite close to the valence band maxima, and number of holes is huge. When and the on p side, the Fermi level is very far away from the conduction band minima. So that's why the number of electrons is very, very small. So that's why holes in majority and electrons in minority. And inverse is true for the n side. Here Fermi level is very far away from the valence band maxima, and that's why holes is very small number and electrons is in large number. And this is what happens in the junction actually. As we look into the Fermi level inside the junction, first the distance between the Fermi level and the conduction band edge starts increasing, which means that the number of electrons starts reducing gradually in the junction here. And at a point, the Fermi level is almost exactly in the middle of conduction and valence band. So here, if you if we sort of calculate the distance between the Fermi level and conduction band minima and Fermi level and valence band maxima, it is almost in the middle. It means that the number of electrons and number of holes in the system is now almost the same and in very small number. Both of them are in small number. And as we go, so this is also the junction point. This is also this point. As we go towards the P side, Fermi level starts coming close to the valence band maxima and number of holes gradually starts increasing. So it means that, so the picture that we obtain from this kind of plot, this kind of diagram, this one, that there is no electron, no hole in the depletion region, that is not true actually, practically. So there are electrons here, there are holes here, but the number of electrons as compared to the number of electrons far away from the junction is very less, because this distance is now more. And number of electrons is exponentially related to the difference between Fermi level and conduction band minimum. Okay. Okay, so similarly here on the P side of the junction, number of holes is less, but it is not zero. And as we go away sufficiently far, as we go sufficiently far away from the junction, the number of holes become very large. Actually, it becomes almost a p-type material. So this is actually what is happening inside this junction in terms of carrier concentration, and so that everything. So there were many questions about the number of electrons, how electrons are distributed inside the junction. That's why I thought of showing you the Fermi level and band diagram of the diode. And this is quite a extremely crucial concept in semiconductor physics, band diagram. Okay. So if the doping on the P side is Na and the doping on N side is Nd, then the contact potential at the junction is given by Kt by Q log Na by Ni square. So more the doping on both sides, more will be the contact potential. And the contact potential in terms of band diagram is also the difference between the conduction band maxima on P side and N side. Okay. This the difference between the conduction band minima on P side and on N side is the contact potential of the diode. There is also an interesting thing that we can observe from the uh, Venn diagram here. This is N-type material. It means that there are a lot of electrons in the conduction band here. So there are many electrons here. This is P-type material. The number of electrons is very small here, almost negligible. This barrier, actually, the barrier between the conduction band minima of P side and N side, this barrier, this hill slope, this stops these electrons to go from N side to the P side. Actually, before joining these two materials, this barrier was not there. As soon as we join, in order to equalize the Fermi level, this barrier is created. So this barrier is what stops the diffusion current. Okay. This is also the barrier that supports the drift current in a way. For example, if there is an electron here, let's say very close to the barrier, it is very easy for this electron to come here because now this movement is favored because the energy is less on this side. Okay. So this is very qualitatively, very sort of high level picture. High level means from a distance, a qualitative treatment of or a qualitative understanding of the diode band diagram that I have shown to you. Now, if there is any question, please ask.
Sir, what is the difference between equilibrium and steady state?
So, in equilibrium is clear, I guess. Equilibrium, everybody has a,
Uh,
every process is countered by a reverse process.
Yes, sir.
In steady state, the difference or the forward process and the backward process, this difference is constant.
Okay,
Which
sir.
means, yeah, which means that if there is an electron flow from N side to P side, and there is another electron flow from P side to N side, this is heavy electron flow, this is light electron flow, there will be a difference between these two flows. So this difference, the net flow, should be constant. It should not change with time. The rate should be constant, which means the current should be constant in the case of diode. But more generally, the flow of the process should be constant in the steady state. Okay. And in transient
Yes.
state, this can be a function of time. Any other question? Because I'm sure by looking at the band diagram, there would be many questions that you might have.
Sir, can you please tell what is the convention used here? CPCN. What is this?
Yeah, so EC means conduction band edge. E means energy, C means conduction band. EC is generally used for conduction band, EV is used for valence band. So EC is actually used for the bottom of the conduction band, means the minima of the conduction band. N means N-type material. So it means that this is the conduction band minima of the N-type semiconductor. And this is the valence band maxima of the P-type semiconductor. Similarly, here it is the conduction band minima of the P-type semiconductor and P-type, or sorry, the valence band maxima of the P-type semiconductor. Here also, EF means Fermi level, energy of the Fermi level. P means on the P side, N means on the N side. V naught is the contact potential. Yeah, is it clear?
Sir, this hill thing shows the depletion region.
Yes, actually, yes. This hill means that this region is broadly the depletion region. This is also the region in which this entire thing is going on, right?
So can you please repeat about the barrier that you told because of this hill?
Um, so when these two, when the N-type and P-type materials are not joined with each other, okay? In that case, uh, the band diagram looks. Can you just give me 1 sec, because I'll show you how it looks like, how the band diagram picture looks like when the materials are far apart from each other. And I guess that would make things more clear. So yeah. So now, do you see slides on your screen?
No, sir.
Now, you see something on the screen?
Yes,
It
sir.
should
Yes,
be.
sir.
Yes, sir. Now it's
Yeah.
visible.
Yeah. So this is the band diagram of p-type and n-type material when they are far apart from each other, when we have not made the junction out of this of these two materials. Okay. Here, as you can see, that in n-type material, the Fermi level is quite close to the conduction band minima, which means number of electrons is huge. And so, in other words, we can say that there are lots of electrons here in the conduction band because of the doping.
Sir, why Fermi level is close to conduction band in N-type and valence band in P-type?
Yes, yeah, that is because the Fermi level is exactly in the middle for the intrinsic semiconductor. Uh, so when we do not have any external doping, the Fermi level is exactly in the middle, which means number of electrons and number of holes is equal in system. As we put more dopant atoms, as we dope the semiconductor with arsenic uh, or antimony, they create more number of electrons in the system because there are 5 electrons. 1 electron is free from the bond and 1 electron is free to move around. So they create a lot of electrons in the conduction band of the system, and that's why the Fermi level is pulled towards the conduction band. As I told you, the distance between the Fermi level and the conduction band minima signifies the number of electrons in the system. Less is the distance, more is the number of electrons. Okay. So this is
Okay.
because of the dopant atoms. Similarly, in this, the dopant atom is such that it is creating more holes. So there would be many holes here in the valence band, and Fermi level comes close to the valence band minima, or maxima, sorry. In the
Okay.
intrinsic material, it should be in the middle. As soon as we join these two different type of, and in this case, before joining, the conduction band and valence band are at the same level actually, because they are the same semiconductor, they are the same silicon semiconductor, so their conduction band, valence band configuration is the same. But as soon as we join them, this is what happens. And this happens because in equilibrium, this is a theorem that we can prove mathematically as well. And I hope you would do that in your second year, that in equilibrium, when each process is balanced by a counter process, the Fermi level must be constant throughout the system. So in order to make the Fermi level constant, so if you are given two such diagrams, let's say, and you are told that you need to make a diagram such that you need to equalize the Fermi level. One condition is that the distance between Fermi level and conduction band on the n side far away from the junction should not change, and similarly the distance between the Fermi level and the junction far away from the junction on the p side should not change. So this is how the band diagram will look like. In order to sort of equalize, or in order to make the Fermi level uniform across this entire system, the bands actually start bending, and this is known as band bending in semiconductors. On the junction, the conduction band and the valence band are bending. There is this change. Okay, and from the what I told you a few minutes back, the number of electrons and holes we can calculate just by looking at the distance between the Fermi level and the conduction band at that point. So in the middle at the junction, the semiconductor becomes almost like an intrinsic semiconductor. So the number of electrons and number of holes both are very less. And that's why it is known as the depletion region. Because now the carriers are depleted. They are not zero, but they are very small as compared to the bulk, as compared to the number that was there in the uh, before joining. So the electrons that were there here, these electrons in the n-type material, yeah, first of all, when we join them together, these electrons, these are filled state and these are empty state, because here the electrons are very less. So electrons will jump here suddenly. Holes will jump here and they might recombine as well in the junction mostly. But very quickly this barrier is created and now the electrons on the n side cannot go here. They are blocked essentially from going from here to here. Similarly, these holes here, they cannot go here. So this is now not allowed. And that's how this equilibrium is actually achieved. There would be a small diffusion of electrons. Some electrons might find some energy because of the thermal energy and they might jump to this side. So this will be the diffusion current and minority electrons here will go to this side. This will become the drift current. And that's how this equilibrium is attained. The diffusion flow is being balanced by the drift flow. Is this clear now? Or anything else that you want to clarify here?
Sir, sir, why is there a decrease in energy from ECP to ECN? Please tell that.
Sorry, can you please repeat?
Sir, why is there the decrease in energy from ECP to ECN?
Okay, why is this slope is there? This bending is there. That's what
Yes,
your
sir.
question is?
Yes, sir.
Yeah, so so the law of thermodynamics enforces that the Fermi level must be uniform, must be one Fermi level in equilibrium. So which means that now this thing needs to come down or this needs to come up. Okay. So this pulls the valence band up along with Fermi level and this pulls down the conduction band, and that's how a single Fermi level is achieved in the system like this.
Sir, it isn't related to the electric field inside the depletion region.
So the electric field, the origin of electric field is actually because of the diffusion. As soon as we combine the two semiconductors, these p and n type, suddenly electrons from n side go to the p side and holes from p side go to the n side. That leaves these uh, atoms alone. These atoms are now without electrons, and that's how this electric field is created. And that is actually the slope of this conduction band is actually the electric field in the system, in the junction.
So, why can't the holes flow from EVP to EVN if the energy is decreasing?
Yes, yeah, uh, that's what I was actually expecting that somebody would ask. The barrier for electrons is a valley for holes, and the valley for holes is a barrier for electrons. So in order for this hole to go to this side, an electron must come to this side. So which means that electron should gain energy. Okay. So generally holes flow in upward direction and electrons flow in downward direction in band diagram. So the band diagram is drawn with respect to the electrons. Okay, so that's why it might seem that holes might be losing energy, but actually it is electrons gaining energy, and that is not easy.
So if the holes lose energy and electron gains energy, will the energy change be zero or will it be increase in energy?
Uh, if the holes lose energy and electrons gain energy, uh, sorry, can you clarify your question?
Sir,
I don't know.
as you said that for a hole to go from EVP to EVN, an electron has to go to ECP. So an electron will gain
Yes.
energy and a hole will lose energy. So will the energy change be zero?
No, 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 no. It is not as if both of them are moving actually. So hole going from EVP to EVN is, in other words, an electron going from EVN to EVP. Okay, so it is not as if both of them are moving at the same time. Hole movement can be visualized as electron movement as well. Okay, so if we in this band diagram, if we visualize the whole movement as electron movement, it means that if a hole is going from EVP to EVN, it is equivalent to saying that an electron is going from EVN to EVP, and it is still a hill for this electron. It is a barrier for this electron to move.
Okay, sir.
Okay, so somebody last time asked about the width of the depletion region. How much wide is this depletion region? And this is after doing the electrostatics of the junction, after solving the Poisson's equation in the junction, and with charge neutrality and all those boundary conditions that you would see in coming courses. This is the final expression that is obtained. So you don't need to worry about these two expressions. Okay, don't worry that they will be asked in the uh, exams, but qualitatively it should be clear that if the number of electrons or if the doping on p side Na is the doping on p side, Nd is the doping on n side. Nd means donor doping and A means acceptor doping. Okay, so more the doping, more will be the contact potential, this potential that is built. And width is not actually directly related to the doping. So width is directly, so as you can see, there is a V naught term here, and V naught also is dependent on Na and D. So in terms of just doping, it has a complex relation. Complex means it is not a straightforward, it is not a proportional or inversely proportional relation. It is uh, there is, however, an interesting observation here that if Na is more than Nd, which means that if p type is doped higher than uh, this n type, or one side is doped higher and other side is doped lighter, the depletion will be more in the lighter side. Okay. So that's the only observation. It is not a direct relation actually. So this is essentially what is the various aspects of carrier dynamics in the diodes. There is one more thing that we need to, since we are talking about the band diagrams. If we apply a forward bias to the diode, a forward bias means this P side is connected to high voltage and N side is connected to low voltage of the battery term. Okay. So the polarity of the voltage, polarity of the battery applied across this diode and the polarity of the semiconductors is same. That is known as the forward bias condition. In that, this will be this V naught will reduce and these bands will start coming up. Okay, so this V naught will reduce and ECN will come up a little bit. So the distance between ECP and ECN will reduce, which means this barrier will, this hill, electron potential hill will now become smaller. So that's why this diffusion current will become stronger. That's the situation in the forward bias. In reverse bias, this hill will increase. And there is a reason behind that. In forward bias, a negative voltage is applied on N terminal and positive voltage is applied on P terminal. Negative voltage means that the electron's potential energy of the electron is Q times V. So the electron's potential energy is actually, so this is the potential energy of the electron, and if we apply a negative voltage, the charge is also negative, the potential energy actually increases. Okay. So that's why on this side, if we apply a negative voltage, the potential energy increases, which brings or which pulls these bands up, including this guy, this Fermi level. So this results in reduction in the barrier and increase in the diffusion current. So now the electrons sitting here, they will find that this barrier is reducing. So they will be, it will be easier for them to go to the P side. Okay. In the reverse case, when this applied voltage is positive on N side, let's say, which is the reverse bias case, in that case, this potential energy of the electron will go down because charge is negative, V is positive. So ultimately it will be a negative number and the potential energy will go down. So which will bring or which will pull these bands down. Okay, so instead of going up, now the bands might come down. Okay.
Sir, the hill goes down in the case of forward bias.
Yes. So the hill height is reduced in forward bias, and in reverse bias, this hill is increased even further.
Yes, education is a fundamental right which should not be restricted to a gender.
Sorry,
Certain-
somebody said something. Hello, can you please say that again? Is there a question regarding this?
So, sir, during biasing, only ECN level increases, N level, N type materials. Like there is no increase or
No, no.
decrease in the.
That is just to sort of explain to you.
Oh, okay.
During forward bias, generally what happens is that we put a battery across the diode, and generally the positive terminal of the battery is connected to the P side and negative terminal is connected to the N side. Generally, we assume that the negative terminal is grounded. Okay. So, which means that the positive terminal is across the P side and this is grounded N side. Or vice versa is also true. We can assume that the positive terminal is grounded and we are applying negative voltage to the N side. So if this positive is grounded and negative is applied on the N side, this is what happens. This does not change, this will come down. If this negative terminal is grounded and positive is at plus voltage, this in forward bias, this will come down and hill will reduce. Okay, so it's essentially the same thing. Is this sort of clear?
Yes, sir.
Sir, from this Venn diagram, can we make sure that what is the length of the depletion layer, that in the forward biasing it is reducing and in the reverse biasing it is increasing?
Yes, that's what is happening actually. That's what actually happens as well. In forward bias, the depletion width reduces, and in reverse bias, it increases.
So from this Venn diagram, can we comment upon that?
Yeah, that's what we can do now. As you
Sir,
can,
because both the levels are decreasing, so the distance between the middle part is remaining the same, so we cannot comment that depletion layer is decreasing or increasing.
no. So if let's say in forward bias, these ECN and EVN are going up. Let's say now, let's say they are here. These are the new ECN, new EVN. So now we need to, in order to make a hill, this will be the new kind of band drive. So this transition region is now actually smaller. This becomes smaller. That
Okay,
is one
so basically
aspect.
the slope is representing the depletion layer.
Yes, and that too, the middle part of the slope. When the slope is very steep, that is the depletion region. When the slope is on the edges, this is not the depletion region actually. So generally, this middle part of the slope, this steep slope, is the depletion region.
Okay, sir, got it.
Sir, can you please clarify again which part is going up in forward bias?
So in uh, forward bias means that the battery that we are going to put across the diode. So the battery will look something like this. We will put a battery here. Okay. So this
Yes, sir.
negative terminal of the battery is connected to the N side, positive is connected to the P side. It means, so we can assume two things here. Equivalently, two things. We can assume that this is grounded, negative terminal is grounded, and we apply a positive voltage. Okay. Or we can assume that this positive is grounded, we apply a negative voltage on the N side, right? Or we can assume that we do not ground anything, there is a relative voltage between the two terminals. These three, generally a battery is described as one of these three cases. These three are equivalent cases. So if a positive voltage is getting applied on P side, its band will come down because positive voltage means reduction in potential energy from Q into V from this expression. And a negative voltage is applied on N side, its band will come up because it means increase in the potential energy. So which means that this gap between ECP and ECN reduces. This hill now is reduced. The barrier is reduced and the diffusion current is maybe more. All right.
Okay, sir. Matlab, in different cases, different thing is happening. If we apply the positive voltage to the P side, then the ECP is decreasing, and if the negative voltage on the N side, then the ECN is increasing. So the overall hill height is decreasing.
Yes, but what I'm saying is that if this battery is, let's say, 0.5 volts, this is a 0.5 volts battery, it will reduce this hill by 0.5 volts either way. These three ways in which we are assuming that negative is grounded or positive is grounded or nobody is grounded, these three are just ways to understand this situation. These are equivalent ways actually. Do you see that or not? If not, I
Yes,
can.
sir. I just wanted to ask like which part is going up or which part is going down. Like when we apply the positive voltage on the P side, then the ECP is decreasing, and
Yes.
the negative
Uh,
voltage on the N
yes.
side, the ECN is increasing.
Yes, exactly.
Okay,
Actually,
sir.
it's all about relative energies. So it doesn't matter which is coming down, which is coming up. Finally, what matters is the difference between the two, difference between ECP and ECN.
And sir, does it
Okay.
affect the valence part or valence band part also?
Yes, yes, definitely. Because the bands, these bands are actually, they move as a whole. They both conduction valence band will go down.
Okay, sir. Okay.
The entire band will go down. It is not just the edges. We are just showing the edges, ECP or ECN. This entire band. So, for example, this conduction band, this is the entire conduction band. Okay.
Okay, sir.
Similarly, here will be a valence band. So, this entire band will be shifting. We are just showing the band edges.
Okay, sir.
Okay, so this band diagram is actually a detailed discussion, but this is a better way to understand and visualize the entire dynamics happening in the diodes, or maybe diode is just a starting point actually. It is also easier to understand things in a BJT or even in a bipolar junction transistor or even in a field effect transistor, MOSFET. So that's why this concept is quite crucial, this concept of band diagram and Fermi levels. Okay. So this is what is there in the diodes, and I have shown you the, or I have broadly given you an idea of when we apply a voltage across the diode. So this is what happens when a voltage is applied. A reverse bias voltage means, from the previous analysis, reverse bias means this hill is increased. Okay, so these electrons that were sitting here, they will find it even more difficult to go to this side. So this diffusion current will be reduced, and only the drift current will remain in the system. And in forward bias, this hill is reduced, so the diffusion current will increase. And or 0.7 volts, current will be, it will to apply any further voltage, increase the voltage further. There is an interesting thing that might happen actually. We are applying reverse bias here, which means that we are pulling this down or up here. What happens if we apply a very large value, a very high value of reverse bias? So if we keep on pulling this up, let's say this side, and if we keep on pulling this down, what happens when the large reverse bias is applied? Any comment what would happen? And on N side, there are many electrons. On P side, there are many holes. Okay. So what happens when this is extremely large? This reverse bias is extremely large, which means that this side has come way below than what is shown in this picture here. What would happen in that case?
So can we say
So
that
there
when
will
we
be a break.
increase the voltage, the ECN is
The
coming
bond.
down and it is coming closer to EVP. So the flow will start from ECN to EVP.
ECN to EVP. Okay. Yeah, somebody else was saying something.
So the bonds of the atoms present in the depletion region will break, and the electrons and holes will move according to the electric field generated here.
Why would the bonds break, by the way?
So because of the extreme voltage applied by the reverse bias.
No, it is not so extreme. So Yeah, so I guess you are talking about avalanche breakdown, in
Yes, sir.
which the kinetic energy of electrons is so high that it is breaking. So it is not so high. It need not be. It is only few volts, 2, 3 volts, or 4 volts.
So when EVB becomes equals to ECN, the electrons in ECN will move to the holes in EVP.
Why? How? Yeah, that's what is already. But how does that happen? If this ECN, so after a certain point, this ECN and EVP will be at the same level, or maybe ECN might even go below EVP as well. But how can electrons sitting here go to this side? Because there is this in between. There seems to be this not a direct path actually.
Excuse me, sir.
Yes.
Sir, I have some doubt that you said that if the difference between EFN and ECN is less, then the number of electrons will be more. So if
Yes.
ECN is coming down, why electrons are not increasing?
No, EFN is also coming down
So,
in
sir, at
bulk.
last, will
Everybody
EFN
is
be of
coming.
different energy?
Yes. So when a voltage is applied, then this Fermi level is not uniform across the device. That's what I told you as well, that in equilibrium, this must be uniform. But as soon as we apply a forward bias or reverse bias, this EFN on, so, so the Fermi level on P side might be different and Fermi level on N side might be different. So there will be two Fermi levels in the system in a way.
So,
Okay.
please, can you give an idea what is Fermi level? Like
Fermi
anything big?
level, yes. So Fermi level is actually, so let me tell you from the basic.
So you are not audible.
Hello, there was some problem on my side actually. Suddenly it got disconnected. Can you hear me now?
Yes, sir.
Yes, sir.
Yes.
Yeah, yeah. I'm sorry because I don't know how it happened, but it suddenly got disconnected. So the Fermi level, you were asking what is Fermi level. So Fermi level, so before going into the Fermi level, let's approach this concept from basic statistics. In solids, or when we combine lot of atoms with each other and make a solid, there are lots of electronic states, allowed electronic states available. Okay, because each atom has certain uh, electronic states, and when a lot of atoms come close to each other, these states are extremely large in number. Now, the available electrons in the solid, they will fill those states. Okay, so those states, the available states, are filled by the electrons in the solid, and this distribution of filling those states is known as the Fermi-Dirac distribution. This comes from the Pauli's exclusion principle. Maybe you might have studied it in your, or you might have gone through it in your 12th or earlier as well.
Yes, sir.
Fermi-Dirac distribution governs the governs how the states are filled inside any system, how the electronic states are filled. And similarly, the Bose-Einstein distribution governs how the bosonic states are filled. Photonics, or how the photons would fill the available states. So in that calculation, in that analysis, there a constant actually comes into picture, and that constant is known as the Fermi level. This Fermi level in physical terms mean that this is the highest state that can be occupied by the electrons at 0 Kelvin. So it is like an anchor for the electronic uh, distribution in the system. So if the Fermi level moves up or down, it means that electronic population will also move up or down. It sort of, it is a constant, it is related to the population of electrons in a certain system. It is also known as chemical potential. And if we add one more electron to the system, this Fermi level will increase. If we take out one electron from the system, Fermi level will change similarly. But it does not change with, it depends on the number of electrons. It does not depend on other things. It does not depend on, let's say, energy, or it is not a function of energy. It is a constant in carrier statistics in fermionic systems, in electronic systems. So
Okay, sir.
here also, in the depletion region, electrons population is getting changed, and that's why you can see that this Fermi level and conduction band are varying. The distance between the Fermi level and conduction band is varying. So, so the point that I was highlighting is that if we apply a large reverse bias in this system, and as some of you actually have rightly pointed out, that if the reverse bias is sufficiently large, there are lots of electrons on ECN, lots of holes below EVP. So at some voltage, both of them will be at the same level. ECN may come below EVP. So that way, on one side we have lot of electrons, on other side we have lot of holes. But in between, there is this kind of barrier is also there. So ideally, the electrons should go to the top of the barrier and then come down, because these are the disallowed. This gap is the disallowed region for electrons. Electrons cannot exist in this gap. Okay, that's why it is known as the band gap. But because of the quantum mechanical nature of electrons, and this I guess all of you know, that electrons can tunnel as well. Electrons can go in the regions where they are not allowed to go in certain cases. So when this region is very thin, let's say this, if this is not a very thick region, and ECN is below EVP, in that case, electrons might tunnel from ECN to EVP. and this is known as the quantum tunneling in diodes. Okay, and this is actually an extremely important phenomenon in diode, and this is the basis of Esaki diodes as well. Some LEDs are based on this principle now. You might not actually realize that some of the LEDs that we are using presently are based on quantum tunneling.
So can you please repeat what is tunneling?
Uh, have you gone through the basics of quantum mechanics in your physics course
No,
or
sir.
in your uh,
No,
okay,
sir.
do you guys have the basic physics course in this semester or next semester?
So it's in next semester, quantum mechanics and statistical mechanics in physics, I guess.
Okay, okay. And in your previous courses, it was not there anyway.
So you mean in 12th
So
standard?
yes, 12th or during
No,
JE.
sir.
So quantum tunneling is actually a quantum mechanical effect. So let me draw this. Okay. So this thing is a barrier, so to say. Barrier means that this physically this might be a wall. And if we have a ball, a tennis ball, let's say, on the y-axis, we have the energy, which means that here uh, this is the this is the energy barrier in a way, and on x-axis we have the physical distance. It is x. So it means if we have a tennis ball uh, and this barrier width height is let's say u naught. If there is a tennis ball whose energy is u and it is striking this barrier whose energy is u naught and u naught is greater than u, then this ball will be reflected back. Do you agree with this?
Yes, sir.
Classically, it cannot cross the barrier because it is against the law of sort of uh, conservation of energy. Because if it is surpassing the barrier, it means that it must have large energy, but it is not having large energy, and
Sir, but
it
what
is
do you mean
against
by,
the fundamental principle.
sir, what do you mean
Sorry,
by the energy of that barrier?
energy means it means in a very rudimentary example, it might be that there is a roof. There is a roof. You want to throw a ball to second floor. Okay. So in order to throw the ball to the second floor of your house, you would need some energy. Let's say you need U naught energy. It means that the energy of the barrier is U naught. Energy of the ball, energy required for the ball to reach to the second floor is U naught. But you are throwing the ball with energy just U naught. Oh, sorry, U. And which means you are throwing it with less energy than the required one. So this might be a potential energy value. In that way, it is a potential energy value. Is it clear now?
Yes, sir, clear.
Okay, so in principle, if the energy of the ball is less than the energy that is required to go to the top of the second floor, or energy of the barrier, it will not reach there ever. But in quantum mechanical particles, if there is a potential barrier, U naught, let's say, and if this barrier is not extremely thick, well, it means that if it is only few nanometers, then these quantum mechanical particles, even if they have less energy than the barrier, they will have a finite probability of crossing the barrier. So if we solve the Schrodinger equation for this case, there will be a finite probability of finding the electron on the other side of the barrier. Okay, can you imagine that?
So that's why electrons were not crossing ECN to EVP even they were having more energy initially.
ECN2, sorry, that's why they
ECN
were
to
not.
EVP, because sir, ECN is having more energy than EVP initially, but as band gap is more, so electrons are not able to cross that barrier.
Yes, so here the band gap is more and this depletion width is more, let's say. If so, if this barrier is thick, then this probability is actually very small. Then it cannot happen.
Okay.
But by design, if we make this barrier small, somehow we dope the semiconductor high, and this barrier is small, and if we bring ECN and EVP at the same level, then in principle they can cross to each other. Actually, the path that they should take is that electrons should first go here and then come down here. Because this is not a allowed region. So this is like a barrier, this inside gap. But because of the quantum mechanical nature of electrons, if this barrier is not too thick, then electrons from ECN can go to EVP when ECN is below EVP. And that's known as the quantum tunneling in diodes. And it is actually the basis of some of the LED devices nowadays, even. So nowadays, you might not actually realize this. You are actually using quantum mechanics in technology. You are using those stuff. Generally, we are not aware of this, but it is happening.
Sir, why electrons do not come to EVN from ECN?
EVN is filled, totally filled. There is no vacancy here. So in order
Okay,
for
sir.
the electron
Yes.
to make a transition, it should also have available states. There is no available state here.
Yes, sir.
Available states are here or here.
Yes.
Okay. So this essentially concludes our discussion of equilibrium diode, reverse bias, and forward bias. Now the diode current, I guess the time is already quite uh, high. So do you guys have anything else? 12 to 1? I'm sorry, I was not planning to extend the class because it gets boring after certain time. But if you agree, can we extend this class to 1 or not?
Sir, we O6 batch is not having any class, but I don't know about any other batch.
Okay. Yeah, let's not maybe a lot of homework. Okay, let's not do it. Let's not. Yeah, please let me know if you have uh, a free slot tomorrow in the first half, 11 to 12, 12 to 1 or 1 to 2, because I might not be available 5 to 6 tomorrow. Okay. So I will not force you to attend class now. So we will start our next class from this on. So now we will see mathematically the IV characteristics of the diode, and after having a brief look at the IV characteristics, we'll go to the applications of diode and transistors. Okay. Okay, so let me know by this evening or maybe by tomorrow morning if you are free tomorrow before 2 o'clock or
Sir,
3 o'clock.
tomorrow there is already all classes from 8 to 6. Matlab from
Yes,
5
yeah,
if you are
yeah.
not taking class.
Yes, if some class gets cancelled, let me know.
Okay.
Okay. Okay, okay, because I got.
Thank you,
Okay
sir.
then. Yeah. Okay. See you tomorrow. Thank you.